Hello guys, after watching this video, you will know how you can use AutoDock Vina to visualize the polar and non-polar residues within your protein, calculate the electrostatic potential of the protein to confirm the appropriate ligand binding sites, slice through the molecular structure of the protein for a deeper insight, and inspect the surface of the protein to look for any visible grooves where the ligand can potentially bind. So basically, we will see how you can critically analyze the structure of your protein to make correct interpretations about it. And after doing all of that, you will learn how you can create a movie out of your protein and ligand to make your presentations and your study even better. So let us begin our session. First, we will open the Autodoc Vina using this icon. You can either register or click on Remind Me Later. This is the GUI for the Autodoc tools. And first, you have to import the protein that you want to analyze. So, for that, you can go to File and go to Read a Molecule. From here, you can load any molecule that you want to analyze, provided that molecule is saved within your computer. Next, you can go to the recent files, and from there, if you have analyzed a protein previously using the Autodoc tools, you can just click on it and the protein will be loaded. Next thing, you can also import any protein of your interest from the web itself. For that, go to Import and select Fetch from Web. You will get the option to choose any of these four databases. Suppose I select PDB. Just add the PDB ID for that protein and click on OK. So it's that simple, and it saves you all the trouble of going to the web, downloading the protein and then fetching it in the Autodoc tools. So everything of that is saved. So you have your protein now. The section that you see here is your protein. 1FYW is the ID of the protein, and from here you can choose the way your protein looks. You can go for the ball appearance or the atomic spheres. Next, we have the ribbon representation. Here you can see the alpha helices, the backbone of the protein, this tube-like thing, and also you can find the beta sheets. Here are the beta sheets and the direction in which it is going, parallel or anti-parallel. Lastly, you can select the molecular surface. This is the one I like the most because you can see the grooves that we talked about. So you can get an idea where the ligand can potentially bind. Now the first thing that we will do is we will look for the hydrophobic and hydrophilic regions within our protein. So to do that, select this inverted triangle right below the color representation. The CL stands for the color, and click on it. From here, you have to select which representation you want to be colored. So currently we have selected L, that is for lines, and MS, that is for molecular surface. So both of these are present here. I will click on MS mole and click on bipolarity. Here you can see that the protein is now colored based on the charge that it is carrying. I will close it. The red color that you are seeing here denotes the negative charge and the blue one denotes the positive charge. And based on the intensity of the color, you can see how much charge it is carrying in the particular environment in which the protein is present. Now that we know the location of the residues within our protein, you can also label them by clicking on the inverted triangle right beneath the labeling menu. From here, you can select either for the atoms or residues or chain or molecule. I want the residues to be labeled for now. I will click on residues and click on name. So here you can see that the name of all the residues are present, and to confirm that we were right, the lysine LYS is colored in blue, while the glutamic acid and the aspartate are colored in red, meaning that the red denotes the negative charge while the blue denotes the positive charge. Understanding the location of positively and negatively charged residues can become highly useful at the time of docking. For instance, suppose your ligand is negatively charged and the binding groove that you think is the correct binding groove for the ligand is also negatively charged. So you can make out that the interaction between the ligand and the protein is not energetically favorable, and you need to look for some other sites. Moving on, the next thing that we will do is we will calculate the electrostatic potential that the protein carries at different regions. So for that, go to compute, then select electrostatics, and here click on compute potential using APBS. So APBS stands for Adaptive Poisson Boltzmann Solver. It is highly used in computational biology studies to map the charge that the protein is carrying. For now, you will not see any change in the appearance of the protein, but if I go to compute again, then electrostatics, and click on map potential to surface. You can select the higher quality if you want and click on OK. Now the protein has been colored based on the electrostatic potential that the different regions are carrying, and this potential ranges from minus 12.1 to plus 12.1. Again, the negative charge is denoted by a red color, whereas a positive charge can be seen by a blue color. This information is again highly useful at the time of docking to confirm the appropriate ligand binding sites. A positively charged ligand will preferentially bind with a negatively charged pocket and vice versa. So based on that, you can confirm whether the groove is suitable for the ligand to bind or not. Now that the surface of the protein has been analyzed, we can also cut through the protein to look for residues that are responsible for a particular property that we are seeing. For example, if we look at this groove, we can see that it is containing a negative electrostatic potential. So we can also find out what are those residues that are giving it a negative electrostatic potential. To perform that, we will go to tools, and here we have to select which kind of representation do we want to cut through. So we can either go for lines or ms mole at this point because we have selected lines and the ms mole surface representation. So because we want to cut the molecular surface and look for the residues beneath it, we will select ms mole, and there are total of 6 clipping planes from T0 to T5, and you can give a try to every one of them to know how T5 is cutting or T2 is cutting. You can just go through that. So for example, I want to cut through the T2 plane. I will select it and then I will click on the icon beneath it. So here you can see that the protein has been cut in approximately half, and if I just double click on it and drag my laptop's touchpad, the protein surface has started to appear again. And if I go backwards, it has again started to disappear. Now you know that the protein has been analyzed and you want this to stop. So to do that, just click on this close menu, close icon, and now you are able to rotate your protein. Now that we can see the residues beneath the surface of the protein, we can also change the appearance, how our protein looks like. So for that, go to dashboard and you can select from any one of them. Suppose I select this ribbon appearance, and let me just remove the lines appearance. So here you can see that the ribbon appearance is there and the molecular surface is present. Let me just zoom it a little so it becomes clear to you. Now we know that where are the beta sheets and where are the alpha helices. Now adding names to the protein will make it even better. So for that, go to label and I want to name the residues. So I have already clicked on it and click on name. Now the protein has been labeled and you can get an idea that which residues are actually inside the protein and forming what kind of interactions and what kind of charge that particular group of residues is providing to your protein. You can just click on clear labels so it is clean again. Additionally, if you want, you can also color a specific representation. For that, go to color and I just want to color the secondary structure, that is the alpha helices and the beta sheet. So I will click on it and you can select from any type of representation that you want. You can select by polarity, you can select by molecule, you can select by chain, Rasmol, Shapley. So whatever you like, you can just click on that and have a good representation of your protein that can be used at the time of your presentations and also at the time of publications if necessary. Actually, this rainbow looks even good. So I will just go with that for now and click on close. So you can perform docking with the help of AutoDock Vina without going through any of these analysis part. The AutoDock Vina will give you accurate binding scores. However, by visually inspecting your protein, you can analyze whether the results given by AutoDock Vina are actually correct or not. You can just validate them with the help of your own experience and understanding. For instance, as I just mentioned earlier, suppose this is the group for the ligand to bind. And here we can see that it is carrying an overall negative electrostatic potential. So this means that the ligand that has to come here and bind must contain a positive electrostatic potential for the reaction to be energetically favorable. So by performing all of these analysis, you can confirm your findings and also convince the other scholars and peers that the results of your docking are completely accurate. In the last section of this video, we will learn how you can add orthosilice and isocontours to your protein for a better understanding of the electrostatic potential at every point of your protein. So for that, we will go to compute and electrostatic potential. From here, just click on display orthosilice. So orthosilice basically tells you what is the potential value at each point, and the benefit of it is that you can move the x, y, and z axis as much as you want. So to do that, click on this grid or volume rendering icon, and you can just move these values anywhere that you want. And as I move it, the potential is also changing. So you can confirm the potential at any point of your protein using the orthosilice. Lastly, you can also add isocontours to your protein. So what it does is, while the orthoslice provides a 2D representation of the electrostatic potential distribution, the isocontours provide a 3D representation, and you can also animate the representation that I will show you just now. For that, again go to compute, electrostatic, and then go to isocontour potential. Now the bigger sphere or the bigger bubble represents a higher charge at that point, whereas the smaller one represents a lower charge. And you can animate this charge distribution by clicking on the animate button here. So the charge is being animated now, and you can just see it how the charge is moving and which are the regions for higher potential and which are the regions for lower potential. So that is it for this video. And in the coming videos, we will be learning how you can perform docking using the AutoDock Vina software. And then we will see how you can create a movie out of your protein and ligand to amplify the aura of your presentation.